So when you see this giant thing, what you want to do here is you want to expand first. So you want to do your rules of expansion, like the exponent comes out in front, division is subtraction, multiplication is addition, those rules, right? And so before I do any type of differentiating, I'm going to apply those rules. So I'm going to bring this 2 in front, right? So I'll have like 2 ln of these, what's inside, right? And then I'm going to expand what's inside with subtraction, right? So I have y is going to equal 2 times the natural log of 2x squared minus the natural log of 4x to the 5th plus 3, right? And then I can actually do it pretty easy, because if you'll remember, the derivative of the natural log of some function is just the derivative of the function over the original function, right? So when I look at this, I can leave that 2 alone, and I can do the derivative of this guy. Well, the derivative of the natural log is just the derivative of this, right? Which is going to be 4x over the original, which is 2x squared. And then subtract derivative of this. Well, that's 20x to the 4th over 4x to the 5th plus 3, right? And I can reduce if possible. So on that first piece, I can reduce. I can cancel one of my x's out, and I can cancel the 2 and the 4 out, right? So I end up with 2 over x minus 20x to the 4th over 4x to the 5th plus 3. The final piece of this is just algebra, right? Common denominator. So the common denominator is going to be x times 4x to the 5th plus 3, right? That's my common denominator. In the numerator, I need to multiply the 2 by this guy. So 2 times that 4x to the 5th plus 3 minus the 20x to the 4th times the x, right? Times the x. And I do still have a 2 that's being multiplied out here. And then I'm just going to simplify it. So I am going to, I'll go ahead and distribute this 4 since it's a 4 out here, right? So I have 16x to the 5th plus 12 minus 20x to the 5th. So then I have a negative, I think they took out a 12, but you don't have to. You can leave the bottom like that. You don't have to distribute the bottom. 16 minus 20, I have, a negative 4x to the 5th plus 12, something like that. Now, with these, you're going to look at your more difficult piece, which is the denominator here. Because remember, this chapter was all about natural logs, right? And so I would use u substitution here. I would say u equals 4x to the 4th plus 5. So the derivative of that is going to equal 16x cubed dx, right? I don't need a 16. I actually need a negative 48. So if I multiply both of those by negative 3, right, then negative 3 du would equal negative 48x cubed dx, which is exactly what I'm looking for. So I know that I can do u substitution here. I know I need a negative 3. That can actually come out in front. My u here is my denominator, so I would say 1 over u and then du. And now I have a really easy antiderivative to do. 1 over u is just natural log when I do the antiderivative. So I have a negative 3, the natural log of that u, and then remember, because there is no upper and lower bounds, I have to do a plus c. And then at the very end, just go back and plug your u in. -3 natural log of my u, and then plus c. And I'm done. That's the end of that. This is actually the same thing. If you think about this, your u would be your sine of x, right? Well, the derivative of sine is just cosine of x, right? The only thing I'm missing is that 4. So if I multiply both sides by 4, I have what I need. So I can say, well, it's going to be 4, 1 over u du. Well, that's just going to be 4 natural log of u plus c. And my u is sine. So 4 natural log of the sine plus c. Very, very simple to do that. Which is actually where we get our derivative of cotangent. So, because cosine over sine is cotangent, and that's the derivative of cotangent. But you don't have to memorize it. You can literally just use substitution. This is, again, really easy. You can think of this as 3 times -1 or times the antiderivative from -1 to 1 of 1 over x minus 3. And since the derivative of x minus 3 is just 1, you don't have to worry about use substitution or fixing anything. If you did, so if you look at some of the others, like 20, the derivative of your denominator there is 2, and you have 5. So you would have to multiply by like 5 halves to get what you need. Does that make sense? Yeah. You have to divide that over. But if you don't have one, it's, you can just go straight to it. So I would say, well, this is going to be the natural log then of x minus 3 from -1 to 1. And then you just plug it in. So 3 times the natural log of what happens when I plug in a 1. Remember, it's absolute value. So 1 minus 3 is -2, but it's absolute value. So natural log of 2 minus when I plug in a -1, that's a -4, but it's absolute value. And you literally just plug those in and you get, your rounded answer there. So this is just doing natural log, but with definite integration. So you wouldn't have a plus c. Remember, the derivative of e to a function is just e to that function times the derivative of that function. All right? So and usually you can't combine them. So for the derivative, I was looking for the derivative of this guy. It's just going to be whatever I was given originally, that right there, times the derivative of my exponent. Well, that's just 15x squared. And I'm done. For something like this, what you're really looking at is, this is my most difficult piece. This is what I want to account for when I do use substitution. So my u then would be the 3x squared minus 4. My du would be 6x dx, all right? I don't need 6x, I need -30x. So I'm going to multiply both sides by -5, right? That will give me the -30x that I needed, right? And this will give me the exponent. And so I'm going to just now use substitution. This -5 will go in front, right? And then instead of e to that big thing, I have e to the u du. Well, antiderivative of e to the u is just e to the u. We're good to go. So we have -5 e to the u. I don't have a top and bottom, so I do have a plus c. And then just fill your u back in. -5 e to the 3x squared minus 4 plus c. And I am done. For this one, if you think about it, your u is still going to be that exponent, right? So my u is going to be this guy, and then this is what I want to account for when I take the derivative of him. So if my u is the cosecant of 5x, then my du is negative cosecant of 5x times cotangent of 5x dx, and then times derivative of that, which is just 5. So cosecant goes to negative cosecant. So sine goes to cosine goes to negative sine, right? Tangent goes to secant squared, cotangent goes to negative cosecant squared, right? And then secant goes to secant tangent, and cosecant goes to negative cosecant cotangent, right? So I have negative 5. I need positive 20 in front of there. So I just need to multiply both by negative 4, right? And that will give me my positive 20. So I'm going to say, well, negative 4 is going to go out here, and I now have e to the u du, right? Well, derivative of e to the u is just e to the u plus c, and then plug my u back in. My u was cosecant of 5x. Negative 4 e to the cosecant of 5x plus c. Again, this is my u. This is what I want in my du. My u is going to be 2x plus 4. My du is 2 dx. I need it to be negative 3, right? So I need to multiply both sides by negative 3 halves. Negative 3 halves. If it's a whole number and you need another whole number, that whole number is your denominator. So like the 2 would be my denominator. What I need would be my numerator. Okay? And that will, yep. So if I multiply negative 3 halves by 2, I get negative 3, which is what I need. So that means my negative 3 halves is going to go on the outside. I'm still going to have from negative 3 to 2, right? And then I have just e to u, du. Well, again, negative 3 halves, e to the 2x plus 4 from negative 3 to negative 2. And then just plug it in. So you can leave that negative 3 halves out. Negative 2 times 2 is negative 4 plus 4, that's e to the 0, minus negative 3 times 2 is negative 6 plus 4, negative 2. And I am looking for an actual number here. You do not have to simplify. Like it will give you a simplified answer and a decimal answer. I literally just want the decimal answer. So feel free at this point to plug it into your calculator. All right, and so when you do plug that in, you get approximately negative 1.297. So if you look on page 413, you'll see area between the curves. For area between the curves, you are literally just figuring out where the two cross and which one's higher and which one's lower. All right, so the first thing you're going to do with these is you're going to set them equal to each other and solve for where they equal each other. So I'm going to say, well, when 2x squared minus 16x plus 30 equals negative 2x squared plus 8x minus 2. So I'm going to see where they equal each other. Okay. There we go. I was actually adding it in my head first is what I was doing. So plus 2x squared minus 8x plus 2. Still not going to be beautiful factoring, but that's okay. Minus 24x plus 5. What did I wrote down that's plus 32. Okay, there we go. This is a 30. That's going to make our lives easier. There we go. All right. Help us to write down the whole 0 there after the 3. That equals 0. Remember, if everything comes out of it, just divide it all out. So divide everything by 4, right? And I get x squared minus 6x plus 8 equals 0. That's much easier factoring. So it's x minus 2, x minus 4, which means my upper and lower bounds are going to be 2 and 4. Okay. So I'm going to say from 2 to 4. Then I just have to figure out between 2 and 4, which one is higher, right? So I would pick like 1. So that's why we're going to be bigger. This is going to be 3, 9, 18 minus 48 plus 30. Oh, that's going to be 0, right? And then negative 18 plus 24 minus 2. So that's going to be positive. So this is 0, that's positive. There we go. Helps to actually do one in between. I didn't want to do one quite as big as they made me. So we're going to put that guy first. We're going to put this guy second. Before you differentiate, combine your like terms. Don't forget you're subtracting. So I have negative 2 minus 2, which, by the way, it's either going to be exactly what you got here or negative of what you got here, depending on which one's first. So it's negative 4x squared. We have 8 minus a negative 16, so that's plus 24x. And negative 3, that's a 2. I just decided to write a 3. Negative 2 minus 30 is negative 32, right? So it's always going to be what you got here or the negative of everything of what you got there. And then I have a fairly easy derivative. It's negative 4/3 x cubed plus 12x squared minus 32x. And I'm going from 2 to 4. And you just plug it in. So plug in your 4, subtract what happens when you plug in your 2, and round it. The chapter 6 that's revolving, okay? So it is, you have the area between the curves in chapter 6, and that's just set them equal to each other and just do basic integration. And then you get to the pi r squared or the 2 pi r h, right? And so those methods are on page 434 in your book. And it kind of shows you if you are in terms of x equals and you're revolving around an x equals, that is going to be pi r squared. If it's x equals and you are revolving around a y equals, that's 2 pi r h. So if they match, then it's pi r squared. If they don't match, it's 2 pi r h. Okay? And so here, I don't tell you, but and then one of them I do, but on the test, I just tell you to revolve it. And you can choose the method. So whichever method is easier for you. Sometimes it's easier to rewrite it and use one, and sometimes it's easier to just use the other. Or you may have one you like to use all the time because of the shifting or whatever, and you're like, it's easier in my brain to do this. You can use the same method. It doesn't matter. So, like for 55, they did pi r squared, which means that my axis that I'm revolving around and my functions need to be the same. So if this is my axis, then these are my functions. Okay? Since I am not revolving around what my two functions are, so these don't match, that means I'm going to have two separate r. It's r squared minus r squared. So I'm going to have to determine which one's, just like I did on the other problem, which one comes first. They give me my boundaries. So that means if my functions are in terms of y, my boundaries are x's, okay? So my boundaries will always match the variable inside the function, right? Does that make sense? So if it's y equals x squared is my function, my boundary should be x equals this and x equals this. So my boundaries are just already set up for me. I'm going from -2 to 0. I have just a pi out here. And so all I really have to do between my two functions is decide which one comes first, okay? And so between 0 and -2, I'm going to pick like -1 and plug it in. If I plug a -1 in here, I'm going to get 5. This guy's always 2, so he's going to come first, right? He's bigger. So I'm going to take this guy and square him minus this guy and square him, all right? If I was revolving around y equals 2, then I would have had both functions inside and then squared it. That's the difference, okay? But I'm not. I'm revolving around something that's separate, so I'm going to square and square, all right? And then that's just a matter of foiling and simplifying. So I'm going to FOIL this guy. That's going to be x to the 4th minus 12x squared plus 36 minus 4. And of course, this guy just is 32. And then I'm just going to differentiate. So it's going to be 1/5, x to the 5th minus, I'm adding and dividing, so 3x to the, was that a 2? Yeah, that was a 2. 3x to, that should be 4, because my new, there we go. and then plus 32x. All right, because I did that right very neatly. And then just go from -2 to 0 and make sure that you multiply your pi in at the end. And again, I'm just asking you to put it in decimal form, so you don't only have to worry about the big fractions. Just make sure you're in decimal form when it's all said and done. I will say this little kicker right here, when 0 is at the bottom, then you don't really have to worry about subtraction, right? Because it's like -0 sometimes. But when 0 is at the top, you have to negate your answer, right? Because it's 0 minus that answer. So just keep that in mind. Why I chose this. So my axis that I'm revolving around is y. These are already set up in terms of y, so pi r squared makes sense, right? Because they're already set up for pi r squared. I do not have both of my boundaries. I only have one of them because my boundaries then have to be in terms of x, right? But I can use this guy right here and plug him in there to see what it would be. If I put a 1 in there, I'm going to see that x equals 0. So that's how I solve for my other boundary. So I'm going from 0 to 2. I'm going to do pi r squared. Now my boundary matches one of my axis matches one of my boundaries. So when I do this, from 0 to 2, if I plug in a 1, this guy's going to be 2. This guy's always going to be 1. So he's first, right? But he goes inside, x squared plus 1 minus my other function 1, and then square it. That's the difference between this guy and the guy above it, right? And so then this is just going to be x squared, and then you take your derivative, 1/3 x cubed from 0 to 2, right? And plug it in. And so that's the difference there between inside, like when your boundary butts up to what you're revolving around versus when it does not. I'm going too fast. So yeah, so square him, take the antiderivative, and then plug in a 2. You're going to get like 32 over 5 times pi, and then you're just going to put it in decimal form is fine. So with shell method, it's really easier to rewrite something like this versus doing that minus something else and shifting it within. Like shifting it, you're going to have to subtract that 5 and then FOIL it with a cubed root. That's hideous, right? So if I saw this, yeah, it is set up for a disk method, right? But it's not worth it. Rewrite him. And so if I rewrite this guy, I just can cube both sides, right? I can say, well, that cubed, so x equals y cubed, right? And so if I rewrite this to x equals y cubed, then my two functions are here, right? Those are my two functions. 1 and y cubed, okay? My boundary, well, I only have this boundary, 0, but if I were to plug in a 1, I would see my other boundary for y is 1, based on that x equals 1, right? So I'm going to do from 0 to 1, and I'm going to do the 2 pi RH. Well, r, if I am in terms of y, is just going to be my y value shifted. So I am revolving around y equals 5 compared to just y value. I'm going to say 5 minus y. If I had been negative, then it would be like y minus the negative because it's on the other side. So think about y being here. If I have y equals 5, he's here. So I subtract my y value. But if it were down here, I would say the y equals 0 is bigger than that. So it'd be like y plus 5, right? If I were revolving around. So my r is just going to be 5 minus that y. That's all the shifting I have to do when I do a 2 pi r method. The height is going to be my two functions. Well, my two functions are now y cubed, x equals y cubed, and x equals 1. All right, those are my two functions. So when I do this piece, I now have to do the same thing I've always done. Between these two functions, I'm going to subtract them in here. Which one's higher from 0 to 1? Well, if I were to plug in a 1/2 and cube it, I would have a 1/8, right? So that's tiny compared to 1. So 1's going to come first, and my y cubed is going to come second. All right? I still have to FOIL it, but I'm not foiling with a cubed root. This is just straight foiling. So 5 times 1, 5 times negative y cubed, negative y times 1, negative y times negative y cubed, and then I have a pretty easy derivative there, or antiderivative. So,